Alright, so this video serves to give you a relatively quick overview of the most important aspects of the topic of entropy. This was covered in April 9th's lecture. If you want to look back at that lecture, I'm going to basically just give you here a summary statement of the most important topics, the things that you need to know for tomorrow's exam. All right, the first thing I think that's pretty important is just to kind of have a general sort of conceptual understanding of this concept of entropy. Entropy, of course, is given this symbol capital S in all of our equations. You know, it's oftentimes referred to as a disorder in a chemical system. It's really convenient to think of it that way. I guess more technically, you could say that it boils down to the number of different ways, or these individual microstates, that a chemical system can distribute or arrange its energy, its internal energy. So we got into a discussion of microstates at that point. Individual microstates were basically a very, very specific snapshot or a very specific way that a chemical system, which can be, of course, very complicated, is able to distribute a given amount of internal energy. And we said that there's a very large numbers of these individual microstates, as it turns out, for any sample of matter. And that's good because nature really prefers to have many different options to distribute its internal energy. However, any one particular microstate was equally possible. So that was one of the things that we learned about in that video. We then went on to discuss, which states of matter, whether it be liquid, gas, or solid, tend to be high entropy states or low entropy states. Generally, gases have a lot of freedom of movement in the molecules, and because of that, gases are very high entropy states. On the other hand, solids tend to be very low entropy states, because in solids, the particles which make up the solid don't have a lot of ability to translate or move side to side. And they're oftentimes kind of rigidly, so almost locked in place. So solids are on the opposite end of the entropy spectrum. They're a very low entropy state. So know that. And another thing that's going to be real important, I think, is to be able to predict how changes in phase impact the entropy. You may be faced with problems where you have to predict the change in entropy, whether it's positive or negative. If something melts or something condenses or evaporates. So know how to do that. It's covered in that video from April 9th, okay? And that really is the next topic. We want to be able to predict the sign for the entropy change for a couple simple processes. Phase changes would be one. This is, evaporation, condensation, melting, things like that, right? Also, if you're given a chemical reaction that produces a different number of moles of gas, whether you make more gas or you make less gas, know how to predict the entropy change associated with those types of reactions. Again, that's all covered in the video, as is changes in temperature, okay? Or else solids dissolving. So any of these simple processes, just be able to conceptualize whether that leads to an entropy increase or decrease for our system. Now, another thing we talked about back in this video is we introduced these so-called standard state conditions. And remember, in the thermodynamic circles, you see symbols that look like this. This would be our standard molar entropy. Well, this 0 right here basically corresponds to the standard state condition. If we see that 0, it means that we're running this experiment or we're talking about the standard state condition. Okay, so know what that is. There's very specific conditions to know for temperature and also for the concentrations or partial pressures of gases. Okay, so you might want to just familiarize yourself with that just to make sure you understand what that standard state is. That's usually pretty important in thermodynamic circles. Yep. All right, moving on then. Also in this April 9th lecture, we introduced the concept standard molar entropy. That's this S0 term. Okay, its symbol is S0. It's called standard molar entropy. And typical units of that are on the order of joules per Kelvin per mole. Joule per Kelvin per mole. Okay, so those are typical units for our S0, which is called the standard molar entropy. And remember, What that corresponds to is I like to think of it as the entropy, which is kind of innately contained within a particular material. It's a little bit of an interesting concept to think about it that way, but it's, I guess, conceptually useful. And then the next question that feeds into that one is about elements from the periodic table. If they are in their uncombined form, do they have zero standard molar entropy or not? Sometimes elements in their uncombined forms for these different thermodynamic variables like entropy or enthalpy or Gibbs free energy, sometimes elements have sort of zero terms which are associated with them. But what about for S0, our standard molar entropy? Is it zero for these elements or not? And what are the typical values if they're not zero? Are they typically positive or negative? Okay, and why is that? And leading into that actually is this next topic, okay? So they're kind of related to one another. I'll let you think it out and reason it all through, okay? But we also learned about the third law of thermodynamics in this lecture. We were introduced to that, and that basically says a very simple statement. It defines our zero reference point for standard molar entropy because it says that the entropy of a perfect crystalline solid at absolute zero is zero. So it sets our 0 point, basically, that third law. And because of that, elements may not have zero, S0, okay? I'll let you look that up in tables and kind of rationalize it out, why elements in their uncombined form may have even positive standard molar entropies. All right, but reason that through in your own mind and have a good grips on that. Next, I'd like you to know general trends in that standard molar entropy value. Again, that should be the S0. Okay, I didn't use a superscript, unfortunately. But no general trends in these values. In other words, how does phase influence that value? If you go from liquid to solids to gas, how does that value tend to change? What about molecular weight? If I increase the molecular weight, how does that influence my S0? Turns out it increases it. What about molecular complexity? If I have a complicated molecule with many bonds between atoms, how does that affect my S0? Turns out more complexity increases my S0. What about dissolving solids? If I take a solid, a crystalline substance, and I dissolve it in water, what impact does that have on the S0? Okay, so all these just general trends were covered in that video from April 9th. It's really easy to ask multiple choice questions about those general trends. Which substance would you predict to have a higher S0, a gas or a corresponding element that's in a liquid stage? And what about molecular weight? If you increase the molecular weight, what's the general trend for S0? So really easy to ask questions about that stuff. So know those general trends. It's pretty easy. You just have to kind of remember it and rationalize your way through it. And then the real big one here is down at the bottom. Don't lose sight of this one, okay? Make sure that everybody knows how to use these summation rules, which we talked a lot in the lectures for chapter 20. Use the summation rules with the standard molar entropy values, these S0 values, to compute entropy changes for reactions. It's pretty likely that you'd see a question based on this one. Okay, so we want to get good at using those summation rules. It's nice because there's really three. There's one for entropy, the S. There's also one for enthalpy, H. There's also one for Gibbs free energy. So we use that same type of summation rule for all those variables. So once you get good at it, it's really easy to remember, okay? But everybody needs to know how to do this at the bottom. This is super important for tomorrow's exam. All right, this just provides a brief overview. Now, obviously, this is just a summary statement of things that you need to know. You really need to go back, dive into this video, dive into the sample problems, just to make sure that you practice enough to be prepared.